Okay, so let us see some problems on queuing theory so that whatever we have discussed would be clear to you. In a railway yard, goods train arrive at a rate of 30 trains per day. Assuming inter-arrival rate follows an exponential distribution and service time also follows exponential distribution with an average of 36 minutes time. Calculate the average number of trains in the queue, calculate the average number of trains in the system. The probability that number of trains in the system exceeds 10 are all the things that we need to calculate. Okay. Yeah. So just look into it carefully. What's been given is clearly arrival rate. Arrival rate. Arrival rate is nothing but lambda, guys, which is given to be as 30 trains per day. Okay, yeah. Next, service time follows exponential distribution with an average of 36 minutes. Means what? For each goods train to get served, it takes 36 minutes is being given. On an average, it's nothing is being calculated. Okay. Service time is being given. Service time, clearly check this. Okay. Service time is given to be 36 minutes, guys. Okay. 36 minutes means what? 36 minutes. I have 60 into 24. 24 hours. In that 36 minutes in 24 hours would be 36 by 60 into 24. Okay. Use the calculator to find out. It turns out to be 0.025. Okay. 0.025 trains per day kind. Okay. Now I need to assess the service rate. I have what? Arrival rate. So I need to assess what is the service rate. Okay. Service rate is nothing but mu denoted by mu, which is nothing but 1 by service time. Remember that. So when service time is being given, I can't take directly. I remember students asking me the question, ma'am, when 36 minutes is being given, why you taking it as 1 by 36 or something like that? Why you're taking it as 1 by 30 and not 30? Actually, for the traffic intensity, I'll be needing the arrival rate and the service rate. If times are being given, I'll be evaluating the rate. How will be the rate? 1 by service time would be service rate. 1 by arrival time would be the arrival rate. Okay. So 1 by service time is nothing but 1 by 0.025. Okay. So 1 by 0.025 is what I will get. It is nothing but, see guys, 0.025 is something between 0 and 1. Okay. Nothing sensible. How many trains are being served? Nothing sensible I am getting. Only if I take 1 by 0.025, it turns out to be 40. Okay. 40 trains per day are getting served. 30 trains are arriving. 40 trains can be served when the service time is 36 minutes for each train, then 40 trains can be served. Now once this is done, it's clear lambda by mu. Okay, so is the traffic intensity 30 by 40? Okay, 30 by 40 is the traffic intensity. You can calculate it or you can leave it as it is. This is traffic intensity. What you've been asked to find out, let's see carefully, guys. I think no twists and turns. Average number of trains in the queue. Okay, so it's length of the queue that they are asking. Also, they are asking the average number of trains in the system. So length of the system is being asked. Of course, the third question, we'll handle it. Okay. Yeah, coming to the first one, average number of trains in queue. It is nothing but LQ, guys. LQ formula, you remember, right? lambda square by mu into mu minus lambda. Do remember? Okay, substitute the value lambda by mu, or you can transform it to rho as well, guys. Okay, yeah. So its answer turns out to be 2.25. See, when I get it in fractions, what I'll do is I'll depending on what to do is I will round it off, guys. I will round it off to higher or lower number depending on the decimals. Okay. Next one is average number of trains in the system. So what is being asked is LS is being asked. What is LS? Just a second, guys. Just a second. Okay, so lambda by mu minus lambda is LS. The first one that we derived in the previous video, you can just check that. It is nothing but 30 by 40 minus 30. Okay, so roughly three trains, guys. Obviously, see, guys, this is a steady state model. So lambda is less than mu, you can clearly see. Okay, that is also one more thing. Yeah. Next thing that he has asked is the probability that the number of trains in the system exceeds 10. Okay, greater than or equal to 10 probability he has asked. You remember the formula, right? It's very simple. It is nothing but lambda by mu power n. N is given to me as a 10, guys. So lambda minus mu, lambda by mu power n is what I need to calculate. Here n is 10. So 30 by 40 whole part. 10 is what I need to calculate. 3 by 4 whole part 10 is what I need to calculate. It is nothing but 0.0563. It is probability, so I can leave it as it is. This is how I will do a problem. Sounds simple, right? Only thing is rho has to be fixed properly. Is it the time or is it the rate that's been given? If time is being given, it is 1 by reciprocal of time gives you the rate, or reciprocal of rate gives you the time. Time I don't need it because it is arrival rate by service rate. So arrival rate and service rate are only needed. So reciprocal of arrival time will give me arrival rate. Reciprocal of service time would give me service rate. Okay. Yeah. Come to the next question. Customers arrive at one window drive in a bank according to Poisson distribution manner with a mean 10 per hour, guys. Service time per customer is exponential with mean 5 minutes. Means what? Each person is taking each person is getting served in 5 minutes. It's taking 5 minutes for to serve each person. The space in front of the window is window including that for the service car can accommodate maximum of 3 cars. Here, guys, he's trying to confuse you saying that it is a finite capacity model. But then there's one more sentence which is very important. Other cars can wait outside the space. So the space is not limited. Infinite space is only there. Infinite capacity is there. So this is an infinite capacity model. Always whenever you are doing a problem, in queuing theory, write first the Kendall's notation. He has given you Poisson kind of thing. Single server clearly has given. Capacity is also infinite. Otherwise, if it's finite, I'll put n here. Of course, whoever comes first will be served first. So first come, first serve is a queue discipline, right? Yeah. Now coming to the problem. Yeah, arrival, what's been given is arrival rate. He has given arrival rate is lambda. That is nothing but 10 cars per hour. Okay. Yeah. Service time he has given. Clearly, I made a mention of it. 5 minutes. Okay. So, It is nothing but 5 by 60. In 60, okay, 5 minutes counts how much is 0.083, guys, 0.038 hours. Now, service rate, that is mu would be 1 by mu 0.083. This is nothing but 12 cars per hour. 12 cars per hour. Guys, again, I'm telling you, make sure first you start with the Kendall notation only. Don't forget, because it fetches you 1 or 2 marks depending on the weightage of the question. Okay. So obviously lambda is less than mu, guys. It's a steady state model. Right. So what has he asked you is, the first question is, what's the probability that an arriving car can drive directly to the space in front of the window? That's the question. Just see here. What's the probability that the arriving car can directly drive to the space in front of the window is the question. When can a car directly, when can a car, just a second. The probability that an arriving car drive directly in front of the window. Okay, what's the probability? It's nothing but P0 plus P1 plus P2. Okay, lambda is there with me. Lambda is nothing but 10 by 12. Okay, which comes out to be 0.834 kind. Okay, so I'll be evaluating P0, which is 1 minus lambda by mu. Once I have P0, I can generate all the other things. P1 is lambda by mu into P0. P2 is lambda by mu whole squared into P0. Okay, so this is nothing but 0.166. This comes out to be 0.138. You can just check. This comes out to be 0.115. Okay, so sum of all these probabilities would give me 0.419. The probability that an arriving car can drive directly to the space in front of the window is, see how many can be there in front of the window? Probability of 0, probability of 1, probability of 2. If there are 0 cars, it's possible. If there is 1 car also, it's possible. If there are 2 cars also, it's possible. Just see here, guys. What exactly is trying to say is, in front of the window, maximum of 3 cars can be parked. Na? So if 1 space is there also, he can park. If 2 spaces are there also, he can park. No. What I mean to say is 2 spaces, no. See, if there are, this is the window. There are 3 spaces. Okay. If there is no car, that is what P0. If there is 1 car, okay, if there is 1 car also, he can directly drive. If there are 2 cars also, if there are 2 cars also, he can directly drive. Okay, that's why what he has done, what we have done is, either if there are no cars, or if there is 1 car, or if there are 2 cars, this is possible. Hence, we have added all the 3 probabilities. Probability comes into picture every time, guys. We can't just forget. We should always link it logically to the things that we are doing. That was the first question, an interesting question. The second one is very simple. The waiting time in the queue he has asked. WQ he has asked, guys. Lambda by mu into mu minus lambda is the formula, right? We have all the values. Lambda is 10, mu is 12, 12 minus 10. That's it. We calculate and get the value. 0.416, something like that is the answer. You can just see this is a direct question. The first one is a bit tricky one. How long is an arrival customer expected to wait before starting the service? Means what? Arriving customer is expected to wait in the queue na. So that's why I have found the length of the queue. Arriving customer has to wait in the queue. Hence, arriving customer has to wait in the queue. Hence, I have found waiting time in the queue. Waiting time in the queue is nothing but 0.416 hours. Okay. Yeah. With this, I will just stop this short video with 2 problems. 2 more I shall do in the next one.